So now we have Shubhram Pandey, also from Heralytics, talking about seerSurv, an R package for deriving post-recurrence transition probabilities in oncology models. So Shubhram, if you want to share your slides.
Yeah, thank you. Thank you so much. Let me share my screen. Is my screen visible?
Yes, thank you.
Okay, thank you. Good morning, everyone. So, in every adjuvant oncology model, we have one transition that we can't fill from the trial data. It's not because that we 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 never fill that, but it's just that because most of the trial don't report it. So one of the numbers like probability of moving from LR to DR. So that is something where we usually put a number and we hope that the reviewer don't ask where it came from. So I'm Shubhram Pandey. I'm lead the modeling and advanced analytics at pharmacoevidence. This is more like a methodology presentation, and the package is something which is just operationalizing it. So what's the problem? The problem is that the model behind almost like this is the model that you can see on the screen is behind almost every adjuvant cost effectiveness analysis. Like we have a standard four states, recurrence free, local regional recurrence, distant recurrence, and death. The arrow here, local regional to distant is something which I'm going to talk about is that because this is something which we don't directly estimate from the trial. It's the per cycle probability that a patient with a low local recurrence goes on to distant disease. And here's the catch that the trials these models are built on don't measure it. Like the big standard trials that we have, like Keynote 54, Checkmate 238, these are the trials which follow patients from the recurrence-free state. So they report recurrence-free survival, distant metastasis-free survival, overall survival, but not the actual transition from local regional to distance. So and the key idea is basically here. So how we can recover these transitions from the data? The very simple idea is that and that's why I usually like it is that patients with a local recurrence live longer than the patients with a distant recurrence. So if you plot both the survival curves, there is a gap between them, and the area of that gap is the average time a patient is spent in the local recurrence state. That one quantity is enough to pin down the transitions. So think about what a local recurrence patient can do in any given cycle. Exactly one of these three things. So either stay in the local regional state, progress to distant state, and then death. So we only have to and the probability, like the sum of the probabilities or in any cycle is equal to one basically. So we only have to solve two, and the third one follows basically one minus the other. So to do this properly, first we have like created a method basically, and then we have also presented it as for, and then now we have transferred that method into an R package so that you can fully use that. So first I'll going to explain what the methodology is, and then coming on onto the package. So basically, what is the input? So for this example, basically we have taken the SEER data, which is like a publicly available data set from the US, and like it has 17 regions, about a quarter of the population. It reports 5 year of relative survival broken down by the cancer record, like local, regional, distant. But one caveat is that SEER reports local and regional separately, not in one. So what we did basically for our example, we blended that like local and regional based on the prevalence, and then we have created one local regional curve, and then we have one which is the distant curve. For each state, we have also fed in the mean age and the sex split, basically, which drive the background mortality adjustment. For melanoma, that's like in SEER, it was about 65,000 local patients with mean age of 61 and around 3,000 with distant. The whole method can be captured in the four steps. Step one is basically we fit the standard parametric distributions, and then we blend the survival curve. So I'll be detailing all these steps in next slide, but here just to provide you a glimpse that first we fit and blend the survival curves. After that, we put the background mortality into it. Then we calculate, like, turn the area gap into the escape probability, like what I told, that if you plot those two curves, you will get the area between that curve is basically the probability of staying in the LR state. Then the step 4 is basically solve for the local to distant rate actually. So and the everything that I'm going to show you, we have run these under different assumptions, like based on the AIC. Like, I know you have a couple of questions that how you blend basically the curves, whether it's based on AIC, BIC, and then so we have performed all these in a scenario analysis. Now, the first step one is basically, why not just pick one distribution and move on? Why we actually blend? So because the data only runs for 5 years, and we need a lifetime curve, and no single distribution is obviously right. So we don't pick a favorite. We fit the six standard parametric models from the NICE guidance, like exponential, variable, comforts, to log something, and generalized gamma. And we let the data vote, blending the best three by their AIC weights. And yes, for the BIC fans in the room, you can switch the criteria. So we have a in the package, we have an argument where you can switch the criteria whether you want to blend based on AIC or blend based on BIC. So we don't take sides in that particular war. For melanoma, the exponential does most of the heavy lifting. So you can see the distributions, like approximately for both distant recurrence and local regional, the blending, the weights is coming out to be approximately 50%, like bit over half the blend. That's the step one. The step two is like a correction that's usually easy to forget, because the relative survival has already taken out the normal background mortality. So it's the survival relative to the matched general population, and SEER gives us the relative survival. So, but our economic model lives in the real world where people also die of mortality. So we multiply each blended curve by the background survival from the national life table. So for this one, we have taken the US, but you can take the life table uh, from any country where you are submitting the model. So that gives us the unconditional survival, the curve you'd actually observe. Why bother? Because if we skip this, part of our gap would have been just the people getting older, and we'd be blaming the cancer for ordinary aging. So the step two is put the background mortality back in. The gap reflects the disease, which is the thing we actually want to measure. Now, coming on to the step three, basically. So this is basically where this idea becomes a number. So you don't recover from the distant disease back to local recurrence, and that's only a one-way process. The irreversibility is what keeps the maths clean. The area between the two curves is exactly the mean time spent in the local recurrence state. We measure it with the trapezoidal rule, or if you like prefer a formal name, a difference in restricted mean survival time, you can say. Then, if the patients leave that state at a constant rate, the mean time is just the geometric series in the state probability, and we solve that for the probability. And for those who like you can't sleep without a uniqueness result, the equation is strictly monotonic. So the equation, like the solution is exactly one, basically. We can't have a multiple solution here. The next step is basically where we actually transition that number, and we calculate the probability basically. So at this point, we have two ways to describe survival in the local recurrence state. One, we build from the transition themselves, like the people still in the state, plus the people who move to distant disease and are still alive. The other we just seen in the slide in the step three is from the CFO. So those two should agree. So we tune the local to distant probability until they match closely as possible, like a one parameter least square fit, with one guardrail, that the chance of progressing and the chance of staying can't add up to more than what's left after general population mortality. So, like in plain terms, the model is never allowed to imply a negative chance of dying, basically, and which feels like a low bar. It's just that we have to solve with that one guardrail. So that's the step four. After we did all this, so now here is the result and how the results look like. So the in the base case, the mean time in the local recurrence comes out at about 144 months, basically roughly 12 years, we can say. The monthly probability of staying put in 99.3%. So that means 99.3% is basically where you are staying in the LR state. And the monthly probability of progressing to distant disease is about two-thirds of 1%. So low band, which is exactly what that's exactly what we are expecting in this disease. So three numbers, three param, and they parameterize the entire local recurrence part of the model, basically, and it's all from the public data alone, no IPD data till now. And here I'm showing the monthly cycles, but the package that you're going to use, you can specify in whatever the time unit you want to, like basically align with your model cycles. So how just presenting from a graphical perspective that how the numbers is look like. So in this picture, you can see the solid lines. Basically, these two are the survival curves, local and recurrence on top and distant below. The dashed lines are the relative survival curves, like without background mortality adjustment, and you can see that it's going on and on. So, and the shaded region between these two solid lines, that's actually 144 months, roughly 12 years. That's actually, we can say that this is the area that gives us basically uh, how much time a patient is living in that LR state. And that's the whole trick in one image. Basically, measure the shaded area and it hands you the transition probability. Uh, Now results etc. So we have also performed some sensitivity analysis, and the question is like, how much does this move if I poke it? So every row here is like a full pipeline, basically from all the steps that we have presented. So in sensitivity analysis one, we switched from AIC to BIC, all other remain same, and it's like barely a free flicker. So it doesn't. In this case, it's not matter whether you are picking AIC or BIC. Shorten the horizon and the mean time shrinks, which pushes the step probability down and the progression rate goes up. Similarly, and that's the right direction basically, where you are like a shorter horizon just chops off the long tail where people sit in the local state for years. The 5 year case, it's basically moves the most because it's living right at the edge of the data. So here you can see it's basically from lifetime 99% to 91% approximately in 5 years. And so that's the sensitivity analysis that we have performed with different horizons and with different approach of weighting. Now the package basically, so it's basically like it's a seerSurv package. So all the four steps are in just one function call, but you can see the results like the intermediate results as well. You just handed the curves. Basically like the LR and VR curves, the demographics, it hands back a tidy object with the three probabilities you can see, which and which distributions it choose every intermediate result, so you can check how it's working. So like I just built it on FlexServe. So I didn't re-implement the survival modeling. I just tested on it. Here you can see on the right hand side, you can also see the different basically the objects like the results, the weight summary, like which distributions assigns how much weight. So uh, now, this is one of my favorite slides because this is like just an honest limitations of this methodology that we are trying to address in the next version. So the first one is basically the geometric series step, like because we have assumed that it's a constant, the patients are leaving the constant rate at a constant rate from LR to DR state. It's defensible here because the curves actually fit the exponential the most, but it won't be everywhere. So at somewhere we have to relax this assumption. The second is basically SEER is the aggregate data. So we are limited to standard parametric models, like no fancy models like pure fraction, splines like that. So for that, we need the patient level that we don't have here. The three is that these are the point estimates with scenario analysis, not the full probabilistic uncertainty like the Dirichlet or something. And it's based on the US data till 2021. So basically, as a next step, what we'll do will keep the more flexible sojourn time distributions to relax the constant rate assumption, uh, proper probabilistic uncertainty by bootstrapping the inputs, and then the cure and spline models, basically, that we can also implement. So these are the next steps that we are planning in this package. So now, in just one sentence, so we take the survival curves, basically from any public data. Here we have used SEER, strip out the ordinary aging, like adjust the background mortality, blend the best fitting models, measure the gap that gives us the escape probability, and then solve for the local to distant rate, all in just one R package. Like, it's a transparent, shareable framework. Feel free to use it and let me know your your thoughts. We have also, so these two are the images that the posters that we have presented. The first poster is basically like on the methodological part, but just one case study, which is melanoma. The second poster is applying the methodology on across the pan tumor, and like it here we have taken almost 11 cancers and all. So the package also consists work on these 11 cancers for now. And when the slide will get uploaded, you can click on these links to go through the package. So before I go, like, this work is like a team effort. So I just take a moment to thank all the authors of this methodology and the package, Sameer, Rashi, Barinder, and Murad. And yeah, that's me. The QR code takes you to my LinkedIn. My email is on the slide. I'm very happy to take any questions.
Thank you very
Thank you.
much, Shubhram. So Dawn had a question about the waiting for survival curves. So you mentioned AIC and BIC. Did you consider
Yeah.
any other options? Because obviously AIC and BIC are, I know you're using external data, but they're based on the data that you have as opposed to the sort of projected period.
Yeah. So basically, in the normal BI, so we have also like, it's not the standard methodologies, but we have also experimented with some other methodologies, like calculating the ESS and then tweaking the formula of calculating the BIC. Like, rather than normal N, we have also added the effective sample size after blending. So that's one of the things which we experimented. But in the package, currently the option that only supports is based on either AIC and BIC. And it's also flexible, like whether you want to blend top three, top four, top two, top, like whether you want to blend all six. That's but so the option is on the number of distributions, but in the package it's currently only AIC and BIC for now.
Okay, and then Lydia had a question about how you were fitting the curves to your aggregate data. So did you use Guyot?
Exactly. So we are running the GEOT algorithm first to calculate the pseudo IPD, and then based on that, we like yeah we fit the curves on that, basically. And that's why we have not gone into the splines and the other one, because if you look into the SEER data, it only provides the 5-year data on an yearly. So that means in total, you only have 5 time points. That's it. So it's good if we only restrict to the standard parametric models rather than going to the fancy distributions.
So Nurhan would like to ask, can you change the background mortality that you're using? So you mentioned US, but can you input your own national data?
Exactly. And that's where like the package currently uses the US one, but it has option of selecting the other life tables, and we are planning to update the life tables basically on an yearly basis in the package. But you can also provide the life tables from the external source. Like, let's say if you are calculating it for Canada, so you can download the life table and you can supply it from from outside. So that's not an issue. The package works on that.
Thank you. And then Ayman has a question. Can you provide references for the randomized evidence informing treatment effects on LR versus treatment effects on DR for treatment XYZ in your example? Ayman, are you able to ask that like verbally? Because I'm not entirely sure what.
Yeah. So I think there are two things going on here. There's you are getting randomized evidence from the clinical trials, and then you are sort of fitting some sort of transition state model to the evidence, and you're trying to infer some sort of differences between LR and DR, some sort of transition. And I'm just wondering, because you're using SEER, so SEER is giving you some sort of baseline from this observational setting that does not distinguish between treatments, but you're sort of transporting some sort of treatment effect from your RCT. So you're making an assumption there that there's a difference between LR and DR. I'm sorry, I'm not a clinician, so I don't understand this. But I'm trying to distinguish here, trying to unpack what you're making an assumption on the treatment effect, but you're sort of getting some differentiation between the groups from the SEER database. So I'm trying to unpack what you're doing over here.
So I think like, and I'm sorry, I still can't get the full question, but I think what you are asking is that uh how we are, because Seer is giving us, like, it's not, Seer is not based on any treatment. Basically, the data is not based on any treatment, so we can't apply these transition probabilities on the treatment in the model. Rather, what we can do, we can like Seer derived transitions is basically represent the natural history rates, we can say. So like if you have in your model, let's say the SOC placebo, there you can apply these, and then based on some relative effect you can calculate the transition probabilities for others. So basically this methods give you a starting point rather than just randomly guessing the number or picking the number somewhere from any source and then defending it. So this methods give you, and see, this is based on Seer. But if you want to change this, and if you want to change this to any other registry data, for example, Australian registry data, UK registry data, whatever, you can use that as well. So this is more like a methodology. Seer and melanoma is just an example here. So you can apply it on any country with the data taken from that country and the life tables from that country, and also you can apply it in your model from the SOC perspective or the placebo perspective, and then apply treatment effect on top of it.
Yeah, okay, thank you. But I think that's a very important point that you should probably point to in your documentation, is that you're not estimating a treatment effect.
Yeah.
That this is just a baseline natural history model, because I think there'll be, if this goes to appraisal, then there'll be some questions about treatment effect, and that's another problem to solve. Thank you.
Yeah. Yeah. Agree. Thanks. Okay. So yeah,
Thank
I
you.
can
At least
see
from
one
my
more
end,
question. I think, yeah.
I think
Sorry,
Donald
it's already
answered
answered.
it. So Donald asked you about the transition probabilities, but I think it was on your last
Yeah. Yeah.
slide. At least from my end, having local recurrence to distant recurrence without a treatment effect, that is an assumption that you could choose to make. So I think that it can, for IAM's question, it can be handled afterwards, I guess.
Yeah, exactly.
Thank you very much.